Hello class and welcome back. So we'll continue on with our course material on electromagnetics. Last week we did chapter 1. It was kind of an introduction and we were introduced to electric fields, magnetic fields, some basic relationships. This week I am skipping chapter 2. We will hopefully have some time at the end of the course to come back to chapter 2 uh, because generally in a lot of textbooks, not all of them, in a lot of textbooks that material on traveling waves is addressed at the end of the course rather than at the beginning. Either way it works, I guess. But for our purpose, I'm going to hold off and look at how our time availability is and maybe address it at the back end of the course. For now, we are moving on to chapter 3, which is vector analysis. And so let me expand this so you can see the full screen. Yeah, so chapter 3 is a very important chapter, although it's basically a review, it's a mathematics review more than anything else. You will notice that we will hardly ever talk about electric fields or magnetic fields in this chapter, because all that we are trying to do is to get a good grip on various aspects of vector analysis, both vector algebra and vector calculus. Now, this is a long chapter. It's going to take me 2 weeks, this week and the next week, to finish it. And for many of you, I will imagine that this is a review. I like to think that all of you have done a course on vectors and some vector calculus also. So think of this as a review, but not knowing when you did this and the fact that the rest of this course depends so heavily on this material, everybody recommends, all textbooks and professors will tell you it's good to take some time and review this just to make sure all of you are up to speed on the ideas here, number one. Number two, different textbooks uh, for this material use different terminology, different ways to present the same ideas. So it's better for us to see how exactly our textbook is writing various things, so that in the future we won't have confusion, about that too. As if you did this course and you used different terminology to represent vectors, then if you did this chapter, you can kind of ignore what you learned earlier and think like this textbook shows us to think. Okay, so with that, I'm going to move ahead and show you that in chapter 3 there are 7 topics, 1 2 3 4 5 6 7, that are from our textbook, and then I threw in a new section in the middle, 3-A, which is kind of a very brief introduction to vector calculus. Now, our textbook does have material on vector calculus that they kind of go right into, but I felt before we do that we need at least a 10-minute review of what's the basic material of vector calculus. So I want to spend some time doing that. Okay, so the first 3 plus 1, the one in blue, or part of the one in blue, we will try to finish today in the lecture recording, and then of course I'll have another recording for examples and problems on this same material, and then everything else, whatever is left in 3A, and then 3 4 5 6 7 will be the topics of the next lecture recording. Okay, all right. So basic laws of vector algebra, orthogonal coordinate systems, transformation between coordinate systems, and then vector calculus and introduction. That's what we're going to cover today. So in topic 3-1, basic laws of vector algebra, we clearly try and define vectors and scalars, equality of two vectors, vector addition and subtraction, position and distance vectors, vector multiplication, and then scalar and vector triple products. Okay. All right. So it's not like you don't know vectors or scalars, I'm sure. And we also did plenty of this kind of material. We called it phasors when we did EE 188 and 280. And you guys did signals and systems, so I'm sure you are also using vectors there. But again, let's start fresh and see how our textbook tells us to think about this. So a scalar is a quantity that has only magnitude. A vector is a quantity that has both magnitude and direction. A field is a function that specifies a particular quantity everywhere in a region. So I'm sure you quite well know scalar vector. What is a field? We'll look at it in a little more detail in the next half an hour. Okay, so most of this material again is from our textbook. I tried to pick the most important points to walk you through. Of course, as I always say, please read the textbook, the chapter in the textbook as often as you can. Try to solve the examples, the exercises by yourself. That will give you good practice. So the important stuff that I gathered, the equations, the figures, the derivation, which generally I don't go into, but here's the important stuff that you absolutely need to know. So starting off with the fact that in figure 3.1 we see a vector, and the way it's written, vector A equals a unit vector times a magnitude, right? A equals A into A, where A, small a is a unit vector, and we have also studied the the method of writing these in the textbook. So small a is written with a hat on top, and a general vector has this bold font. It's darker than the other, and when you see just a light font, no bold or no hat on it, that is a scalar quantity, and that generally means the magnitude. Okay, so in general, vector A also has a direction as shown here, and the unit vector also has a direction. Okay, so this is not new, but here's how it's shown. Now, a unit vector can also be defined as the original vector divided by the magnitude, right? So that's what you see here. A is a unit vector, and the big A, bold A, which is the vector, can be written as A times magnitude, or unit vector times its magnitude. So if you take A to one side, then you get A by mod A, or magnitude A, which is also A by A. Okay. Now A is generally in the systems that we are studying, it's in 3 dimensions. Sometimes you'll see only 2 dimensions, x and y, but generally everything we are doing in this chapter and the future is 3. So you have x, y, z, and you can see how normally we write A in one system called the Cartesian system or rectangular system. So we'll study more about these and other systems, but for now let's start off with defining A as written in this form. Ax, Ay, Az are called the scalar components along the x, y, and z axis respectively, and you can see in the figure how Ax, Ay, and Az are shown for A, which is the vector here, right? The vector A starts at the origin O and it goes to a certain point, and this is how it's represented in 3-dimensional form. The base vectors, also known as the unit vectors, are shown just like it's shown A here. Here we show x, y, z with a length of exactly 1, or unity, right? That's why they're called unit vectors. So how do you write a vector? You write it in this form. The unit vectors, which are in bold, x, y, z with a little hat, multiplied by the scalar quantity, which is this length along each axis. Okay, so I hope you can imagine from this three-dimensional figure what ax, ay, az mean. So if you want to find a, which is the magnitude only of this vector a, then you write that as mod a, and then you do the root of ax square plus ay square plus az square. Similarly, if you want to find the unit vector, now it may have a magnitude of 1, but it can be, we are not trying to find the unit vector along just the x-axis or the y-axis, but the unit vector for a, the main vector, and that is this formula a by a, which we saw here, which comes out to be this. Okay, so basically you're taking the original vector and just dividing it by its magnitude. So it still is a vector and it still has three components in three directions, x, y, z, but it's different from the original vector. As we do more problems, you're going to get used to all this. So let's move on. Equality of two vectors. A and B are equal only if everything about them is equal. That's what it says. Ax has to be equal to bx, ay equals by, az equals bz. The unit vectors a and b also have to be equal. So if and only if a equals, magnitudes equal, the unit vector equals, and the scalar components in the xyz direction have to be equal. Vector addition and subtraction. Now we did some of this as part of our phasor analysis, so I don't want to go too deeply, but there we probably didn't do 3 dimensions, so here we have 3. So if you have a which is in 3 dimensions, x, y, z, and you have another b, another vector which can be written like this in x, y, z, then you can add them using the parallelogram rule or the head to tail rule. Okay, for most of our usage, this example or this form is pretty useful. So if you want to know c equals a plus b, then you just add the two scalar coefficients ax bx, ay bay, az zc, and then put the xyz in front of each one and you get the new c. What is d? You can just do a minus b, which is a plus of minus b. So you can take minus and b and put negative in front of every one of these, and that can also be written in this form. So you can do it graphically using the parallelogram rule or the head to tail rule. I won't go too deeply into that. This is a slide I just stole from my own presentation from EE 188. It was slide 9.12, and I show you how you can do a graphic calculation of R, which is a resulting vector. In this, there we called it phasor, to do a minus b. So you see a, b, first you reverse it and do a minus b, and then you can do the head to tail rule and come up with the value of R, which is the resulting vector. Okay. So far, we don't have to worry too much about this graphical method. I don't know where we may use it later on, but it's in the chapter, so we should learn it. Okay, moving on, slide 9, summary of the basic laws of algebra. Well, I guess I should say laws of vector algebra. So a plus b equals b plus a. This is the commutative rule. In multiplication, this is for addition, this is for multiplication. Multiplication, it is a scalar times a is nothing but a times the scalar. Associative, a plus b plus c is also a plus b plus c. Similarly, k into la is kl into a. Distributive, k into a plus b is Ka plus Kb. Okay, so these are some important laws of vector algebra that you'll use quite often, and hopefully by now you're familiar and comfortable with the meaning of all that. So here's a topic called position and distance vectors. So in fact, what we've seen so far, the way we defined A as, uh, unit vector times its magnitude, is also a position vector, because we always uh, start at the origin and end at a point. But what you'll notice here is these three scalar quantities, ax, ay, az, is actually a point in space, and it's written in this way. So you see point and the three coordinates 3, 4, 5 on the x, y, z axis, which are these quantities. Now, this is from another textbook, this figure. I thought it explained things a little better. Sometimes when I find some other place is a better figure or definition, I just try and steal that and bring it into here, not to confuse you, but to show you that, different ways of thinking exists about the same material. And you may go into another situation where you don't exactly follow what you learned in the textbook, but it's slightly different because someone else learned from a different textbook, right? You don't want to be confused. The main ideas are still the same, but the way they're written could sometimes be different. And I can tell you in vector algebra, definitely different textbooks use different approaches. So for example, in this textbook or in this figure, ax, ay, az are unit vectors along xy, xy, and z. And they are shown like this. Instead of showing them as x hat, y hat, z hat, there's no hat here. They're just written as ax, ay, az. So you can see how this vector a is written like this, rp, and p is the point it's going to from the origin, and it's written with the ax, ay, az and the coefficients 3, 4, 5, which are the coordinates of this point. Okay, so that is important to understand. Now I brought in a little extra stuff here, not to confuse you, but this is important and I didn't see it anywhere, so we might as well learn it here. Okay, here's a little more note that says illustration of position vector rp, which is 3ax plus 4ay plus 5az. So sometimes, now this kind of a vector is called a constant or uniform vector. Why? Because the coefficients are numbers 3, 4, 5 and they're constant, right? If you'll often run into, in fact, the bulk of this course, you're going to run into many vectors that look like this. The coefficients of ax, ay, az, or x hat, y hat, z hat, will not be numbers 3, 4, 5, 8, 9, 10, minus 1, 2, 3, whatever, but they will be in variables xy, y, xz, t, and so on. Such a way of writing a vector is, then it's not a uniform vector or not a constant vector, and I don't think there's a name for it, but, or let's call it a non-uniform vector. But this is very common, and a lot of problems you're going to solve will have this format. Then we say vector A depends on space variables x, y, and z. Okay, these are variables x, y, z, they are not constants, and A is composed of these kind of coefficients. So here's another definition I saw, which you probably should become familiar with: vector field. Okay, so an example of a vector field is a vector in three variables x, y, z, and it has, again, each of these coefficients is a function of x, y, z. So, and also note that it's written as ijk in this case, right? So you've already become familiar with three ways of writing the unit vectors. Our way in our textbook, x, y, z; another way, ax, ay, az; And then the third way, I, j, k, each of these are unit vectors of length 1 but along each axis, and they're all perfectly okay, right methods of writing. And depending on the textbook, depending on the writer, any method may be used, and generally you won't be confused. But again, a vector field is like this. Each coefficient itself to xy, y, xz. A lot of times we'll use field or the variable being t in time, just one variable. So there can be one variable, there can be two variables, there can be three. It can be xyz, it can be, t, length, etc. But every coefficient is a function of multiple variables, space variables. Okay, so I wanted to introduce you to that early enough so you don't get confused when you see it in the future. I'm going to move on. Slide 11, continuing on the idea of position and distance vectors. So we just saw a position vector, right? For example, and now this is back to our textbook. When you see these kind of figures, you know we are back on our textbook because our textbook has a certain way they draw the figures, which is pretty nice. But you can spot it when I'm back on our textbook. So P1, for example, is a point x1, y1, z1, and the vector that connects from origin to P1 is r1, and so r1 is written like this. Similarly, there's another point P2, R2 is written like this, and with that little arrow, it shows a position vector. Now, what is a distance vector? So if you want to find a vector that describes the path from P1 to P2, such a vector is called a distance vector from point 1 to point 2 and is written like this, R12. So it has two little digits here in the suffix. So R12 is P1 to P2, and it's generally derived as R2 minus R1, which is you take the difference of these two vectors. And hey, the simple way to do this R2 minus R1, unless you want to do it with a drawing, is to just take the difference of the scalar coordinates on the x-axis, y-axis, z-axis, x2 minus x1, y2 minus y1, z2 minus z1, put the unit vector prefix xyz, and you get the resulting vector. Okay? So you created a vector that shows the path from one point to another. It's a distance vector. But let's say you just want to know what is the magnitude, right? How far away is P1 from P2? Then all you need to do is to take this magnitude of this vector, the distance vector, and to do that you can use this formula. I mean, if you already derived it, then just do the magnitude. But if you are still working in x1, x2, y1, y2, z1, z2, then you can also find it in with this formula. Okay? All right. I'm going to move on to another topic. I think for some reason this wasn't in our textbook, or maybe it's somewhere that I couldn't find it. So I just brought this from another textbook. Okay, so what is a projection or a component of a vector? So let's read this. The scalar component, this is a scalar AB, of vector A along vector B. So you have two vectors, right? You have a vector A and you have a vector B. So the component of this vector here is this little quantity AB. And what is that AB? It's a scalar quantity. It can be derived as A into cos theta, which is the angle between A and B. And it's also written as magnitude A times magnitude of AB, which is a unit vector in this direction, times cos theta, between the angle between the two. Another useful formula to find this value is A times AB. So how to use these? We'll do some examples and you'll learn. But just remember that when you have two vectors, you'd often talk about the component or the projection of one vector onto another. So here is a scalar component definition, and there can also be a vector component definition. So what that is just this AB, but now we show it as a vector, and so you have to add to this AB. If you put a little AB in front of it, this AB is a unit vector, then you call that the vector component AB of the vector A on B. So they're basically the same thing, but one of them is a scalar, one of them is a vector, and they both connect two vectors, together, A on B or B on A also. Okay, so this is important. Another very important factor, and this will probably actually, let me move this here, and here is a important rule that I should definitely highlight so that you remember it. Oh, what happened? Oops, I'm wasting time here. Okay. So any vector A can be resolved into two orthogonal components, one component AB parallel to B and another A minus AB perpendicular to B. Okay, so you can see that here, if you have a vector A, one component is this AB, right, which is parallel to B. In this case, actually on top of B. That is a vector component, and then there's another component A minus AB which is perpendicular to B. Okay, so just keep that in the back of your mind. You'll realize as we do some problems that it is an important property. Okay, moving on, the simple product, we are in vector multiplication now, so that's 3-1.4. So there's two types of products. Actually there's three, but let's generally ignore this and then we look at the two here. So a simple product where you multiply a vector with a scalar. So you have A, what is B, which is k times A? You just multiply that k, or use that k, which is a simple number, and every coefficient, scalar coefficient, gets multiplied by that k, and then you write the whole result in vector form, and that's called a simple product. So that's one multiplication. Now when two vectors are multiplied, right, A and B, now you have two types of products. One of them is a scalar product, also called a dot product, where you put a dot B. Another type is called a vector product with a cross, or a cross product, so where you put a cross and a B. Okay, so these two types are important and we'll spend some time learning more about them. When three vectors A, B and C are multiplied, the scalar triple product also exists and is written as A dot B cross C, and a vector triple product is written as A cross B cross C. Okay, all right, moving on to slide 14. More details on scalar and vector products. So a scalar product is a scalar quantity. Scalar or dot product is a scalar quantity, and here are the formulas that you need to know very, very well. A dot B is AB cos theta AB. A dot A square, is A square. The magnitude of A is this. You can derive it. I mean, we know how to do the magnitude, but you can also derive it in this form. More importantly, theta AB between two vectors that we know the dot product, it can be derived like this. Okay, and we'll use many of these formulas later on, but for now at least become familiar that they are here and in your textbook, and be prepared to use them. So very important formula, A dot B is just the product and the sum of the individual scalar components along x, y, and z. Another important thing, if they are at 90 degrees to each other, A and B are called orthogonal and their dot product is 0 because cos theta is 0. So here's some figures to show you, the same ideas. AB, how to look at angle theta AB, how to angle theta BA, etc. Positive, negative, depending on the magnitude of the angle. Lastly, the dot product obeys both the commutative and distributive properties of multiplication. So A dot B is nothing but B dot A. Similarly, A dot B plus C is A dot B plus A dot C. This is a distributive property. Okay. All right. Moving on to cross product. Now, a cross product results in a vector. Previously, dot product was a scalar quantity, just a small number, right? But here, you're going to get a vector as the result when you multiply a vector and a vector. And you'll see that a little unit vector appears in front of this formula, and instead of cos theta, now we use sin theta. Okay? And this n is a unit vector normal to the plane containing A and B. So if you have A here and B and the two are on one plane, then n is at 90 degrees to the plane. And when any vector is at 90 degrees, we don't use perpendicular, we don't use the word perpendicular, although sometimes it's used. But the right way to say it is it's normal to the plane. That means it's at 90 degrees like that. Okay. Here's a bunch of other formulas and rules. A cross A, 0. Unit vectors, each of them along the xyz, if you take their cross product with themselves, it is 0. But if you take a cross product in this form, in this order, then you get the other. So x times y, you get the other, which is z. Y times z, you get the other, which is x. Then z times x, you get the other, which is y. Okay. Last but not the least, very important, we finally, you see that a matrix appears. So far, we have avoided matrices in all the courses that at least I've done. Maybe you've done it in other courses, like signals. But here, we finally see a matrix, in fact, a determinant appear. And so, if you want to do A cross B, the easiest way, I mean, you can remember this formula, or the easiest way to write it is write xyz on the first line, write the coordinates ax, ay, ab on the second line, second row of the matrix, then bx, by, bz on the third row, and then do the determinant. I hope you know how to do the determinant. If not, this is a good time to practice. It's here, it's shown here also. You take this x and then multiply ay, bz minus by, az, which is here. Similarly, you take ay or y and then you multiply these two, ax, bz and bz minus, actually there's a minus sign. It depends how you do it, but this is the, generally I put a minus here in the middle and then flip these signs around, but you can do it this way also. And then with z, this coefficient, you do ax, bz minus ax, by minus bx, ay. Okay, so I hope you're familiar and that this is not strange and new, but that's a very important to understand how it's done and be able to do it quickly. Okay, couple of rules, same formula, same figures here on the cross product. The cross product is anti-commutative. What that means is A dot B or A cross B is minus B cross A, and then A cross B plus C is A cross B plus A cross C, which is the distributive rule. Okay, scalar triple product. Again, you see the determinant form here. Now, when you do this triple product, you end up with there's both a scalar version and a vector version. And you can see that A dot B cross C is B dot C cross A, C dot A cross B. And how to find one of these? You write the three coefficients again in a matrix form, do the determinant, and you will get a scalar quantity, which is the scalar triple product. A vector triple product, on the other hand, there's no shortcut. You have to first do B times C and then do A times that result. Or you can follow this method, which is a little bit easier. It's called the back cap rule. But it's important to know that there are two different triple products, scalar and vector. Okay? All right. Well, we come to the first of the examples, which I will skip. We'll come back and do this later. So we got example 3.1, example 3.2. I have a problem, another problem from the back. This problem is from somewhere else, but this example 3.5 or problem 3.5 on slide 21. We'll do this later. We'll do this later. We'll do this later. Okay. Now we are on section 3.2 called orthogonal coordinate systems. Okay. Slide 24. So we have our introduction to orthogonal coordinate system. Then we study three forms of coordinates. One called Cartesian, or also called rectangular. It's the same thing. Then we have cylindrical, and then we have spherical. So what exactly does this mean? Let's proceed and learn. So what are orthogonal coordinate systems? An orthogonal coordinate system is one in which the coordinates are mutually perpendicular. That means they are at 90 degrees to each other. So when we say x, y, z in 3 dimensions, what we have studied so far, each of the axes is at 90 degrees from each other. Apparently, there are many other systems where they are not at 90 degrees. Luckily, you and I don't have to bother about that in this course, or maybe in all of your undergrad engineering course. So we'll just stick with orthogonal systems. Now within orthogonal, as I've said, there's the Cartesian called rectangular, the cylindrical, so I am showing you a little coffee can to show you what a cylinder is, and a spherical system. A sphere is like a soccer ball, so that's a spherical system. So we have three systems that we are going to study. Now this table, where it looks very complicated, but it's the summary of everything that we are going to study in this chapter or in this section 3.2.0. So all the formulas have been put together in one place, and this makes life very easy when we start to solve problems. Some of this is calculus at the bottom, which we will only cover in my next recording of the lesson, but the algebra stuff is right here. Okay? All right. So with that introduction, let's move on. Now everything we have studied so far, these figures are all from the rectangular or the Cartesian method or coordinate. So I'm not going to repeat it. I just put the two figures to show you that we already know about it. So let's move on to cylindrical coordinates. Now this is new. And again, I'm putting my little coffee can here. Now one thing I will say again, this figure is from a different textbook, but I think it explains this whole cylindrical business a little easier, so I brought it here. So forgive me that we have our unit vectors are not shown as, x hat, y hat, z hat. They are shown in this form: a rho, a phi, and a z. But this point P in a cylindrical system, now the three axes, although the x, y, z is shown here, but the way we write it in cylindrical coordinates is rho, phi, z. Still we are talking about three coordinates, right? But instead of linear x, y, z coordinates, we have rho, phi, z. So z is still the same in both systems, but we have new items here, rho and phi. So what is the significance of this rho, right? So we have the same point P, and rho is the distance from the z-axis, right? So if you imagine that in the center of this can you have drawn the xyz axis, then the point from the z-axis line to one point on the surface of the can, which is this P, that distance is called rho. It's a distance. So here we have a distance rho, a distance z, and the other coordinate in the middle, the center coordinate, is an angle, phi. What is that angle? You can see from this figure. It still depends on the xyz system to define it, but this angle from the x-axis to the y-axis of this line that is drawn from the z origin to the point P, that angle is phi. So the definitions of these rho, phi and z are like this. Rho is the radius of the cylinder passing through P, or the radial distance from the z-axis. Phi is called the azimuthal angle. You may not need to remember this word, but you'll see it maybe a few times. Phi is called the azimuthal angle and is measured from the x-axis in the xy plane. Z is the same as in the Cartesian system. Okay? So, a rho, a phi, a z are unit vectors in the rho, phi, z directions. And here's the values that the rho, phi and z can take. Alright, so that was one way to introduce you to this coordinate system. Here is what is in our textbook. Now as you can see, this figure is a lot more complicated than this figure, the previous figure. But because we have to study from our textbook, there's no avoiding it. Here we go with our textbook. Now in our textbook, instead of using rho, we are using r for the first coordinate of the cylindrical system. So r phi z, and the same definitions are here. You can see the figure gives us a little more detail. There's the z plane, the phi plane, and then there is a cylinder at r equals r1 for this point P represented in the cylindrical coordinate system. Okay, so spend some time, and of course the three unit coordinates, the unit vectors, are also shown here in the figure. So become familiar with how you're drawing the r unit coordinate, the phi unit coordinate tangential to this circle, and the z, which is the same as we had seen previously, but they exist and they are of length 1, but they are in different directions than what you're used to in the xyz system. The mutually perpendicular unit vectors are r hat, phi hat and z hat. Okay? Alright, gotta move on. In cylindrical coordinates, a vector is written as a equals a hat times magnitude, which now we write as r phi z, which are the unit vectors. Then the magnitudes, instead of calling them ax, ay, az, now we call them ar, a phi, az. And there's other formulas and rules. I will let you become familiar with them. And now I'm moving on to spherical coordinates. Spherical, we think of the situation where we are discussing like a soccer ball, right? So here, this is a little piece of the soccer ball, right? What you're seeing. You can complete the drawing, which you can see here in other figures. But again, this is from another textbook. I brought this here to illustrate to you that the same point on the tip of the soccer ball or the surface of the soccer ball is now represented using one distance r, which is not the same distance as this, by the way. So be careful. In the spherical, it's different from what we read in the cylindrical. In the spherical, this r is the distance from the origin to the point P. So here's the definition. Then there are two angles, one of them is theta, one of them is phi. So phi is like the theta of the previous system, but theta itself is a new thing, which is this angle, which is the angle between the z-axis and the r vector, or the r, I guess the vector from O to P. So become familiar with this and the terminology of spherical coordinates. So point P can now be represented. Look at this figure from our textbook. So there's a point P with coordinates r1, theta 1, phi 1 in the spherical system. And what does that mean, right? So here's the meaning. So you can see r is the distance, theta 1 is an angle, this angle, and phi 1 is an angle between the x, it's on the xy plane, this one, okay? And this forms a conical surface. The unit vectors are now shown as big R, theta, hat, phi hat, okay? So these are the three important systems that we have to study. In the spherical system, it's written like this. And as you can expect, once you have three systems, you need to be able to go between them, which is the topic of our next recording, along with some problems. So I have to break, we are running out of time, but I'll come back, finish this theory, and then we'll look at some problems.